So linear equations are used in the real world to model things. They gather data and they plot the data points and scatter plot. They make a scatter plot, and then they say, oh, this looks like a linear model, and so they come up with a formula for the regression line. So that's what we have here, and they gave us the data. Here's this big chart, and they're talking about global warming and the concentration of carbon dioxide parts per million there. Okay, so they gathered some data. They said, well, there's 317 average carbon dioxide concentration in 1960, and the temperature was 5704. And then they took a data point in 1970 and 80, 90, 2000, 2009. So that was the last data point there. They took all these data points. So like this point right here would be 317, comma, 57.04. And then they plotted those points over here on this graph. So there were, I think, 6 points, 6 data points. And then they drew this kind of purplish line there that kind of estimates what that model would look like. Now, we're going to get the equation of the line. What's important here is that we use the points actually on the line. Don't use the other points. Use the ones that they tell you, okay? So use those points. All right, if we want to find the equation of the line, we'll have to find the slope. So we're going to take, this will be like our y sub 2 and our y sub 1. So we're going to want 50, I think it says 57.99 minus 57.06. And we're going to divide that by, and this will be our x sub 2 and our x sub 1, which is going to be 385 minus 326. Okay, so we're going to get a calculator and we're going to see what that is. So, oops, 57.99. Oh man, should just like do this on my own time. Minus 57.06. I do like to let people know though what we're putting in the calculator. So 0.93 is what I get up there. Hopefully I did all that right. And then we're going to have 385 minus 326. And we get 59. And so I get 0.93 divided by 59. And I'm getting, well, it's 0.0, it's about 0.01576. So we're going to round that off to 0.02. So we're going to use that for this slope, and it is positive. We're expecting it to be positive. It's an increasing function. Okay, now we're going to use that, and we'll use one of the points. I would use the smaller point, probably, with point slope. So y minus y sub 1 equals m times x minus x sub 1. And so I would have y minus 57.06 equals 0.02 times x minus 326. Okay, and then what form do they want it in? Well, they probably want it in function notation. So I would get y by itself, and that's what we've done in the past anyway. So y minus 57.06 equals 0.02x minus, I got to do that multiplication, 0.02 times 326, 6.52. And then I'm going to add the 57.06 over. Let's see if I'm leaving something out. Okay, and I get y equals 0.02x, and then I'm going to have 57.06 minus 6.52, and I have 50, whoops, plus 50.54. And so then that would be the equation for the line, okay? All right, so that would be like a model, and you could use that to predict things. Now, that's what we're going to do in this next section. It's a little wordy, but in the real world, that's kind of what you're facing, is trying to take the information and apply it into, what you're working with here. So we have a model. We said X, and Y. X was representing what? The number of carbon dioxide, CO2, per thousand or per something. What was it? Per million parts. Okay. So the X is the amount of carbon dioxide, and Y was the temperature. Okay, so keep that in mind as you go to apply this. It says in part B, the pre-industrial concentration of atmospheric carbon dioxide was 280 parts per million. The United Nations Intergovernmental Panel on Climate Change predicts global temperatures will rise between 2 and 5 degrees Fahrenheit if the carbon dioxide doubles from the pre-industrial level. Compared to the average global temperature of 57.99 in 2009, how well does the function from Part A model this prediction? So we're going to use what we had in Part A. I'm going to scroll up so we can do that. Y equals 0.02x plus 50.54. And then what we want to do is we want to find out when the carbon dioxide concentration doubles, what would the temperature be? Okay, so we're doubling this. We're doubling what the pre-industrial concentration was. So what's twice the amount of 280? That's going to be 560. So we want to let X equal 560. So we're going to double what it was pre-industrial concentration, 280. So double it, that's 560. And then we're going to find out what our model says the temperature would be. Now, I can put that all in my calculator. So you kind of have to say, well, what does my model do? It takes the number of carbon dioxide concentration, takes that number, and gives you the temperature. Okay, that's what it's calculating. So 0.02 times 560 plus 50.54. And I'm getting 61. So I'm getting Y to be 61.74. That is the temperature then. So they're saying the temperature, if you doubled the concentration from pre-industrial and made it 560, the temperature, according to our model, would be 61.74 degrees. Now, the question says, how well does the function predict this? Okay. So if you look at 57.99 in 2009, we don't know when it's going to double, but when it doubles, will it be between 2 and 5 degrees more? Well, if it happens, since 2009, and now the temperature is 61.74, what's the difference then? What's 61.74 minus 57.99? Well, I don't know, so I'll just grab my calculator. 61.74 minus 57.99. And it's about, that difference is 3.75 degrees. So is that between 2 and 5 degrees? Yeah, so it would increase by about 3.75 degrees, and that seems reasonable. They predicted it'd be an increase between 2 and 5 degrees. So model does predict temperature well, I guess. It says how well does it? Well, it does a pretty good job. Okay? That one was a little tricky.